HNSW is one of the most widely used algorithms for similarity search in modern vector databases. It is popular because it offers an excellent balance between speed, accuracy, and scalability, even when working with millions or billions of embeddings. However, while HNSW works well out of the box, its real power comes from how effectively it can be tuned. In this video, we'll break down the three most important HNSW parameters: EF_search, M, and EF_construction, and explain how each one affects search quality, latency, memory usage, and overall system cost in real-world Gen AI systems. Let's start with EF_search. The EF_search parameter controls how many candidate nodes the algorithm explores when a search query is executed. You can think of EF_search as the amount of effort the system is willing to spend at query time to find the best matching vectors. When EF_search is set to a higher value, the algorithm explores a larger portion of the graph. This increases the likelihood of finding the true nearest neighbors, which improves recall and result quality. However, this also means more similarity calculations, leading to higher latency and increased compute usage. On the other hand, a lower EF_search value limits how much of the graph is explored. This results in faster query responses and lower cost, but it may miss some relevant vectors. In production environments, EF_search is often tuned dynamically. Latency-sensitive applications such as real-time chatbots or recommendation engines usually prefer lower EF_search values, while analytical or high-accuracy workloads can afford higher values. Next, let's talk about the M parameter. M controls the maximum number of connections each node can have in the HNSW graph. In simple terms, it defines how densely connected the graph is. A higher M value creates more connections between nodes, making it easier for the search algorithm to navigate through the vector space. This improves recall and stability, especially in high-dimensional embeddings. However, higher M values also increase memory usage and indexing cost. Lower M values reduce memory footprint and indexing time, but they can make the graph harder to navigate, which may reduce recall. An important thing to remember is that M is usually fixed at index creation time. Changing it later typically requires rebuilding the entire index, making it a critical design decision. Now let's look at EF_construction. This parameter controls how many candidate nodes are explored while building the HNSW graph during indexing. In other words, EF_construction determines how carefully the graph structure is built. A higher EF_construction value allows the algorithm to consider more candidates when creating connections. This results in a higher quality graph with better neighborhood relationships, which improves search accuracy later. The trade-off is that indexing becomes slower and consumes more memory. The key difference between EF_construction and EF_search is timing. EF_construction is a one-time cost paid during index creation, while EF_search affects every single query. For this reason, many systems choose a relatively high EF_construction value to build a strong graph, and then tune EF_search based on runtime performance needs. These three parameters do not work in isolation. EF_construction determines how good the graph is, M defines how richly connected that graph becomes, and EF_search controls how aggressively the graph is explored during queries. Tuning only one parameter while ignoring the others often leads to suboptimal performance. In real-world applications, different workloads require different tuning strategies. Semantic search systems may balance EF_search and M to achieve fast responses with acceptable recall. RAG pipelines often increase EF_search to ensure relevant documents are retrieved, even if latency increases slightly. Recommendation systems usually tune M carefully to stay within strict memory and latency budgets. One common mistake is relying entirely on default parameter values provided by vector databases. Defaults are designed to work reasonably well across many scenarios, but they are rarely optimal for specific datasets or workloads. Another mistake is aggressively increasing EF_search without measuring the actual improvement in result quality, which can unnecessarily increase cost. Key takeaways. HNSW parameters allow vector databases to balance speed, accuracy, and memory usage at scale. EF_search controls query time recall, M defines graph connectivity, and EF_construction determines index quality. When tuned correctly, HNSW enables fast, accurate, and scalable similarity search for modern Gen AI applications in RAG systems. In the next video, we'll dive deeper into RAG architecture and explore how retrieval pipelines are designed end-to-end. If you found this video helpful, then like and subscribe to the channel for more Gen AI deep dives. Thanks for watching.